What do you think if we start with out of all these out of all these files, I call one best presentation. It doesn't have a PDF sign. I mean, it's crazy. But anyway, it's as long as okay. Manfred, are you paying attention? No, you're not looking at it. You see what's on the screen? International Rectifier. That's when I presented it to International Rectifier when they licensed this patent, and now Infineon has taken it over, okay? So you better not make a note and report to the company what you saw. All right, so here is, how do I get this now? Where is it? Oh, okay. I did have a warning for charging, so you better charge this computer too. So
no, it's fine. It's fine. Yeah.
It's fine. Okay, how do I get here all the slides?
You can click down here.
No, I know that, but can I get all the slides on the side so I can jump from one to another out of the order? You know, like the whole.
Not sure. Does anyone know how to do that? Click on the arrow. View.
Which one?
View. Go up. Yeah, view. Yeah. And
page navigation.
go to remote.
No, it's PowerPoint has built in that you can opt to have all of them on the side, and that's
There's page navigation. There's an arrow on the left.
where?
Oh yeah, on the left.
Yeah.
Oh, here.
Yeah.
Okay. Oh, yeah. So that hides in some, and mine doesn't. So, and now you click on this, and it'll give you the. Yeah, that's what I was looking. So it's big enough. Now, can we put this on the whole screen? We don't need scrap on the other side, right? You know, so this here and put it on the whole page. How do you eliminate it? Huh?
There's an arrow. Not down.
Yeah.
Oh, all these little hidden gadgets. Okay, cool. And I think I can also move this a little bit. Yeah. So you can see. Okay, fills up the whole screen. All right. Let's start with the first one. That's obviously old, but I kind of limited the number of, these are different groups for the IR. I'll skip those. I didn't care about that. Hybrid switching method and step-down converters. That's what I'm talking about, okay? Let's go to the next one and say hybrid switching method, capacitive energy transfer and single resonance PWM combination, okay? Let's start with a buck converter, famous buck converter, okay? Very simple, inductor, transistor, and a diode. Problem, how to insert, of course this is part of another thing, how to insert AC isolation transformer by using additional switches. One thing I wanted to do is make a buck gain function with a chuk type transformer, and that's what it does, okay? So what I do here, I go to the next step and put a capacitor here, and you see capacitor is being charged. Inductor is increasing, voltage is increasing on capacitor with this current. And then next step is, if I turn this switch off, what happens? Well, there is no place for there is no place for current to go. So you couldn't do this switch and this switch put over here, right? So you need another switch here, because mainly what capacitor needs, it has to be charged and discharged. So now I'm giving him a discharge path with another switch. Now you say, why are you doing so crazy thing, Dr. Chuk? Well, because I have obviously want to have two complementary switches on input, which be rated as input voltage. You know it, right? And then if I somehow can split this capacitance like in a chuk converter into two capacitors, voila, here's my isolated nuk-buck, right? And has a step-down characteristic D something and no input inductor, right? Okay, but this won't work because, why? Because when I discharge it, it's going to be, chaotic discharge. Because in this loop, you know when you short capacitance, what happens? You have 100 volts on it, you short capacitance, have you seen it? You know, and then there is all kinds of current because capacitor says, I want to be discharged. You know, give me the shortest possible time. You know, physics, right? But we can prevent that discharge, which is of course bad because when you multiply with the frequency, this is all the losses. Let's put a famous resonant inductor someplace. Where can we put it? well, it's here. What is the next one? I think
7.
this one here. Yeah, it shows. So next one is this here. Well, if I put a resonant inductor, I can put it in a series with a diode. This is a concept which in the past we did put additional switches and additional resonant inductor with it. And I think that my next one, I hope that my next one shows that. Well, if you have here, if I put this resonant inductor, this is a loop, right? Let me discuss that. In this loop, I could put a resonant inductor here, here, and here. Agree? If I put it in a, this is active switch. That's no. Because active switch, you know, I have to make sure that the current through that resonant inductor is 0 before I can turn it off. If I turn it off before that, switch will explode. We'll have a big voltage and kill the switch on the voltage stress, right? But is any problem having a diode in series with the inductor? That's the key of my new line of converters and switching methods and so on. There's no problem because diode says, hey, I'm conducting still current and don't bother me, right? Okay? So there is no problem having a diode here. Okay? Now, there is a problem having diode here in the active switch, but is any problem having diode in series with a capacitor? Not really, because it's a leakage inductance of 200 nanohenry and this is 5 millihenry inductance. I mean, who cares, right? So, okay. So, but what happens in this loop? Capacitance was charging, and now it's discharging. Okay. Then I think, let's go back where this whole thing is. Because I'm giving a bunch of the concepts now which you probably never seen before. I hope so. So this is the one which we are showing here, right? And the point I will also say is this. At this point, look at this design. It's discharging and circulating loop. But you say it's useless. From energy transfer point, it is not lossy, but it doesn't do anything because you're charging it and then you're discharging inside the loop. Neither input sees it. That's good. It doesn't go to the input because, believe me, some of these people copied and rated my other patents and the ideas, and then they get a capacitive energy transfer, and all this energy they put in a capacitor is discharged back into the input. So nothing happened, and it looked like a flyback converter. Okay, well, they don't know what they're doing. That's a problem. Okay, so but here, this is still not a good idea, but it has a better way, and you'll see why I have several versions. What happened when I grounded switch? I cut this connection, and if I put it down into the output, what happened? I got to go for free over the discharge current. Yes, it is discharging, but it's discharging to the output. Bad news, I can't do isolation transformer anymore, you know, here, because I cannot split capacitor into two, get isolation, because it's now connecting this switch from a primary to the secondary side. But, you know, hey, I'll first investigate what I can do with the non-isolated converters, right? And you know what that tells you? If I put this, total charge and discharge have to be the same. If I put all the charge to the output and now all the discharge, I also put the output, what does it say? I have twice much current to the output, twice much power, right? And what happens? My stresses in this circuit and one which is connected to the output, voltage stresses are the same. Current stresses are the same, except I deliver twice the higher current and twice more power. So what happens? Magic. I went from this converter, which is, say, 80%, whatever switches are and so on, it becomes 90%. I mean, where can you find a topology? And that's why I'm saying topology is number one. Where can you find a topology where you just change one connection and now it becomes from 80% 90% or from 90% to 95% and so on. Now when we go to 99%, I'm sorry, I can only give you 0.5% to 99.5%. But that's okay. That's a different story. All right. So now we have two concepts. So we go now to the next one. And what is this next one? You see here, we move this resonant inductor from a diode. We moved it into this branch. Okay, not much, still the current. And this is why I call it a hybrid switching method, because you have a PWM method. Capacitance is being charged linearly, and then you have a then you have a second interval when it's resonant. And of course, they have to match. There is no initial, and that was what I was explaining on a demo. You know, because a leakage inductance of that transformer in in a ČUK-BUCK2 converter, what happens? It's in series with a capacitance, and it creates this resonance. And resonance has to be continuous. There is no jump. And that is the key difference between these two patterns. One of them shows this resonant inductor. When I move this into the other leg, shows it, and it causes a jump, like a smaller, but nevertheless jump in that version of converter. But guess what? Its beauty is in the simplicity, right? You know, this final version doesn't have to have external inductor, a resonant inductor. It works only on its own leakage inductance, absorbing it, and at the same time you don't have to build it. Okay, it's part of the circuit, and it doesn't have a jump, so there are no losses. You see here, this here is a smooth. You know, the end of the inductor current here is rising linearly, a resonant current, and then is discharging in a resonant way, and both points are well connected. You know, there's nothing happening there. It's smooth, right? Okay, so we go to the next one. Ah, here it is. This is what I just told you. The switch is moved from here into the output. Okay. And here's all the charge is moved to the output, right? But now, so we said 80% become 90% and so on. Let's now move to the next one. Ah, here it is. Very little change. Okay. What are the change from the previous circuit? Well, just say, oh, okay, instead of having diode here, I will move the diode on a tap, and here's my tapped inductor. Not much difference, right? But a huge difference in the performance and what's happening. I don't have any more resonant inductor here. I depend on this inductor, and that's hybrid transformer. I can use a large step down and moderate duty ratio, 1/3, half, and so on. So what happens if this is one turn? You know, that's what I said before, but it's not obvious. If this is one turn and 100 amps on the output, right? Because that's the only thing connecting to the output. Plus, there is some help from here. But let me tell you, this is not any more important. Can you see why? When 10-to-1 turns ratio is here, is it important? Because this current, primary current, because it's 10-to-1 step down in the voltage, but it's a 10-to-1 step up in the current. So that resonant current on the primary is going to be 10 times smaller than the current already coming in here. So I'm adding 1/10 of a current extra. So who cares? So I can now go back to my original, right? And then connect this to the source. And whatever. I have a high side driver, both grounded switches, everything is fine. Well, I lost the 10% of improvement and so who cares, right? But what I gain is that now, also, you see in this loop, when this capacitor is here, I always marvel how Intel would buy for $10 this VRM converters based on a buck converter, and they have a $1,000 processor. And then what happens if the main switch on a buck converter shorts? Tell me. If the main switch shorts, you know, you're going to get all these 12 volts on the output, and you're going to fry the $1,000 microprocessor. What about here? If I turn the switch on, is this capacitor, is this voltage going to go to 12 volts suddenly? No way. Because why? The capacitor, there is a capacitor divider between this way, and a capacitor divider, if this ratio of capacitance is 10-to-1, you know, you basically will, even if this is constantly turned on, of course this is down at the ground, this will never show, the output will always show 1 volt. Doesn't matter if it's short, permanent or not. Okay, hey, you're saving your $1,000 processor for one thing, because especially the 100 kilohertz or megahertz, you know, if it turns on and you cannot turn it off and it fails, bad news. But anyway, that's just a side issue. So now we go to another one. And this is that was one with the resonant transformer, which you cut it off. So I will actually not go into much detail. Blocking voltage. Yeah, let's go to this one here, original. If the turns ratio is 10-to-1, for example, what is the voltage that this diode sees? At 50% duty ratio, the diode sees 1/2, twice the output voltage. So if output voltage is 1 volt, the diode is rated for 2 volts. And these two switches, they can be 48 volts. They're rated for 48 volts. How bad is that? And those two switches, when next one is down to ground, they are in 0 voltage switching mode, you know, and you don't have a spike. You have as you saw it, right? I showed it on a simulation. So therefore, that's it. And I will actually just show you this best simulation, best presentation, a few more till 20, and then I release you and invite you this afternoon at 5 o'clock to hear the whole thing, okay? So let's then go. So that's one thing. This one is rated low voltage, high current. And you know what? In a buck converter, they are proposing 48 volt to 1 volt, and 48 volt has a 50 voltage spike because there is a hard switching. So they use a 100 volt switch on the input for 1 volt output, 100 amp. How much is that? That switch, synchronous rectifier switch, is seeing 100 volt and seeing 100 amps. It's a 10 kilowatt switch for a 100 watt output. How does it make sense? And you are going to see a bunch of presentations here of all these gallium nitride companies showing that nonsense, okay? And they're not going to stop until someone tells them. I'm telling them, okay? And you got to support me on that, okay? You're my crew. You're my crew on the boat. We got to get out of this, how you say, disaster. It's like on a sea. There is a big storm, and we are now in a big storm. The whole power electronics is in trouble. I'm telling you. So. But I will say that in concluding remarks, remind me, but let's go here. So we go further, and I do. Okay. One thing which also happens, which you remember I promised to tell you that. Look at this here. One converter modification has a unique feature. Converter output can adjust each switching cycle automatically to the DC current demanded by the load. You saw the DC load is forcing the peak-to-peak sine wave current. And you know what you see here? Look at it. This is a switch current. This is a secondary current. And because I'm summing the switch current, second switch current, and secondary current, and this is a current on a load. How does it look to you? Okay? Doesn't it look like a perfect sine wave with a little glitch here? You see, if you make this kind of overcome over this, wasn't that like a regular sine wave? When I saw that on a scope, I said, my God, I have a digital scope. What do I do? I just put it on a digital scope, save this waveform, and what I do then? Shift it by half a period, exactly half a period. And what do I get? I get a Tesla working again. 2 sine waves shifted 90 degrees out of phase. Three-phase sine wave add to 0, and 2. And this here in this case was better than Tesla because it's only for 2-phase. You know, it's like 2 sine wave out of phase cancel, right? That 2-phase doesn't exist in Tesla. There's a 3-phase or 4-phase, which is a half of 4-phase is a 2-phase system. But anyway, but you know what's the beauty? I changed the load current suddenly to half, and what happened? The sine wave peak to peak is half of a peak to peak. So do you trust me now that that the step load change will be fantastic? Because step load change changes, and the next cycle, the other half is just doing that. Okay, so that's the thing. And I have only a few more which are very important to show. This is if I put this in parallel, you get this here, right? And you get essentially that these are high current. But if you add them together, the ripple current on the output is small. You don't need capacitance. And you're actually making the same converter and making the second converter phase shifted by half a period. How bad is that? And you don't need those gazillion capacitors and 8 buck converters and still don't get it right and all the problems, right? And I showed you the primary capacitance are nothing, right? I mean, carrying the tenths of the load current, right? And little chip capacitor, okay? Now, so that's the end of it. And I just want to show you one thing on this. Where is this other? This one?
The presentation folder.
Huh?
Everything is on this folder again.
Oh, this one. Okay. Just one waveform. Be patient. I know you have other places to go, so I will take this appendix waveform. Okay. I just want to point out 2 key. I made a big deal of this step or so on, so I want you to see that. You see, this is a again. Well, now this one doesn't show. This is a different kind, I guess. You know, it doesn't matter. So we can go. This is basically. Oh yeah, it's here. You have to start. It looks like okay. So you go like this, and let's move on. Here, this version where inductance is here, or this version for that matter, it has a waveform of the switch. Watch this waveform. Still has a jump, because that inductance is not in a series resonant extra resonant inductance, not series with the capacitance. Only series connection with the capacitance. Capacitance says I cannot change instantaneously. I'm sorry, and it starts wherever it charging finishes, or capacitor starts a resonant current. Okay, which is what we need, right? So now that's one waveform of this configuration, and I go further down, and I have this waveform, and this also shows how nonsense is you can use a tap inductor, but you ever analyze tap inductor for voltage gain conversion? You use on a tapped inductor, not only because it's bad, so bad anyway, but if you use a tapped inductor with large turns ratio, here is n is equal to 2, n is equal 4, and n is equal, basically this for this converter, but I think for a tapped inductor, it all starts, I don't know if I have it here. No, I don't. But actually what happens, on a tapped inductor, all the waveforms, 2, 4, 6, 10 times, they all converge, and they all end up with 1. And what it means is that you really, at the 50% duty ratio and lower, it doesn't matter whether you use a 5 to 1 or 10 to 1 step down, who cares? You're not getting any step down. Whereas here, in those converter, that is using 2, it's here, and when you, and in fact, in the other one, you have more and more waveforms. The more turns, the more it starts. Well, basically, step down is 1 over n times d. So you get a full step down. In a tap inductor, you get nothing, okay? Or very little, let's say 10% or so. But anyway, so now this is what I want to show you, and I'm going to conclude this with this part. This is a waveform where we don't have the extra branch, okay? I mean, the main switch is down to ground. Resonant inductance is in series with it. And guess what? This green waveform is my output current, and this is a current transformer. So the ratio between output current and input current is just the ratio of total number of turns to the input turn, okay? And therefore it's only in magnitude. So both primary current of the tap inductor and secondary is continuous, no jumps. And that's the key difference. And what? That's much better circuit anyway than the other one with extra resonant inductor, with the extra going to the output, and we don't gain anything. I just showed you as my process of thinking that initially I thought I'll gain something, and I did gain if I have a separate inductances, 2 resonant inductances, but once I have a tapped step down converter in voltage, and I'll tell you now the final why this combination of the two. Tapped inductor provides a step down in the voltage and step up in the current, okay? But it comes with the steps. And then this transformer, which has a primary, and I think if you show here, here, let's show this. This current here is an AC current. It's a funny thing. It's not like a Faraday transformer when I put an on time, an off time, like a 60 hertz sine wave. It's a positive cycle, negative cycle. Everything, the AC waveform is happening during the off time period. You see what I'm saying? It's the tapped inductor requires on and off time to work as a step down. But because capacitor and resonant inductor is series on a primary, they create resonant currents which has 0 level. So it has to go negative and positive. So it's an AC current. You see what I'm saying? So now that that's why I call it hybrid. That transformer, Faraday kind, work a little bit different than Faraday's because it's not excited. It's excited by that AC current and it's current transformer. So whatever is current on a primary and 10 to 1 turns ratio, current on a ripple current on a secondary 10 times increase. And what happens? It's a summation of step current of the tapped inductor and a continuous current of the AC currents of transformer. When they add them together, they eliminate a jump on a primary and jump on a secondary, and the magic works. Okay? All right? So that's that is basically my conclusion. There are many different ways how you can do that. And this is shown here. You see? Yeah, that's this waveform. Okay? Green waveform is here. Other waveform. This is a current on input. This is a on a switch 2, on a switch which goes to the output, and then input switch, and so on. But combination is that these currents which we have a switched part, they just match to make this primary current continuous and secondary current continuous. And that's what makes the whole magic works, okay? And you can make a 400 volt, 48 volt to 1. I have an isolated version that I can put isolation transformer which brings it from 400 volts to 48 volts, and then this another tapped hybrid transformer breaks down to 1. So I have no problem making it 400 volts to 1 volt. So why should I really even have 400 volt bus, 48 volt bus, when I can have a 400 volt bus with low current and no leakage and so on. Okay, getting back, my conclusion is, see me this afternoon. I will tell you one thing. I don't know if we have a, can we get on a, for 1 second, can we get on internet here? Or you have actually a Wi-Fi. I hear there is a free Wi-Fi for the whole thing, right?
It's a little bit slow, but you can try to connect that. I don't know if
Free internet, instant internet open.
one which says free. Okay, it does disappear.
Huh?
Okay.
Free internet open, right? Connect.
Let's try to see if it works or not.
Connecting, okay?
Personal hotspot maybe.
Okay. Okay, thank you.
What is that? Oh, you can Wi-Fi connected to the?
Yeah.
I think that would be cool. Just 2 minutes, trust me, and then I'll let you go eat. I see you're all hungry.
Should be
yeah, you can
wishes
find it.
phone. So can we find that? Can we do it around the Wi-Fi?
Yes, it's on. Just need to.
Close mine. You don't need a presentation. Close mine.
Yeah, this way. You choose.
yeah,
Okay.
Yeah.
Yeah.
Okay. And then enter this password.
Yeah.
Are you connecting?
It's connecting. Okay. Let's see it works or not.
Oh, yeah. It's put CNN or whatever.
Oh, it works.
Hey, hello, voila. Okay. Thanks to Yushi Liu. Okay. What it says 1988? What does it mean?
It's some error. Actually, I'm from COPEC, University of Colorado and Boulder.
But 1988, what does it mean?
That's my born year.
Oh, I thought it was a conference you attended. I'm sorry. Okay. Then I don't want to tell you year I was born. Okay. So, but okay, we can put a here. Is this already? Okay. Okay. .com. Okay, hopefully get there, right? Did I press enter?
No, you have to click on.
Huh? Oh, I see. Okay. Well, here we are. This is my website. Between today and tomorrow, you can got, well, I think I don't, just like, what is this? We can put the whole screen. And, let's say go to home. Okay, this is the home screen, and I think news, download. Oh, I don't. Actually, what you should be able to get on it, I have. Yeah, here it is. What I was talking today is put in a different way. It's more like a teaser. That's what I'm going to put on my website. Short versions of these talks without the details. And if you're interested in detail, you can go in my. This downloads will be called Institute. Why? Because I just started last Friday. You know, had a crazy idea of his trilogy, three parts. I'm started my on a LinkedIn group, Power Electronics Institute. I come from a California Institute of Technology as a first institute, so this will be my second institute I work for. So now on that institute, here is this article, and you can see this, and you see the text, and you see another pictures which compare the two. You will see this tonight at my exhibit, comparing the two, and on a poster hopefully, and then you have my presentation at the people, Brazilian people like me. You know, it's funny. You know, they do like me. You know, and this is my 1 hour presentation they gave me to introduce this new technology. I was an opening keynote speaker. Okay, first day, and they don't like me in the United States, and they don't like me in Europe. You know why? Because they don't like the message. They want to kill the messenger because they don't like the message. And I had a fantastic time in Brazil, and you know what? My next paper will be spec 2016, and in December in New Zealand. Southern hemisphere is not yet infected with these viruses that everybody's in a committee, everybody's in committee and writing the papers and preventing others. I'm serious, and you will see some really backlash of this because I want to stop that. Look, last time I presented an APEC, I was invited by a lady who asked me, hey, let's celebrate 35 years of the U.S. State Space Averaging. I expected, made presentation, and that was 2010. I don't go to this conference. I go once in every 2 years, because why? Every time I submit the paper, it's either not approved and stolen, which is happening with what is here, or mismanaged and so on. So I don't have any need for it. So I'm now starting my own Power Electronics Institute. Connected with that is my web page. We'll have my past articles on the institute, and I have my own YouTube channel. You want to go to my YouTube channel directly instead of this? Just type. I have a weird Serbian name, Slobodan Čuk, C-U-K. There is very few connections, so if you print that on YouTube, you'll get to my channel. No sweat. If you want to go to Amazon to get the books, on my books, type Slobodan Čuk, and you'll get directly to my books, okay? So that's one advantage. But I think I'm tying together all three. I'm looking for feedback from you guys, what I'm doing, because it's always necessary, and I'm looking for support, obviously, through that, through Power Electronics Institute. And that's going to be directly, tightly connected with this, so you'll be able from there to see my presentation. These basically are chapters of my Volume 5 book. And my Volume 5 book is Power Electronics, New Beginning, okay? And my Volume 6 will be Power Electronics for 22nd Century. That was actually the title of my presentation, which is in Brazil for 1 hour. And that's a presentation where I wanted to give improved presentation here, and I was not allowed. I was not good enough in my 42 years of the Power Electronics experience. And with all of what I contribute here, I was not allowed to be one of the 5 plenary session presentation. I don't want it anymore, okay? Thank you very much. Okay, I said it. All right, thank you. And see me in exhibit booth. Remember, I love that you showed up in big numbers. I said my enthusiasm and presentation goes exponentially proportional to the number of audience, okay? So I want to see live bodies, including some girls, okay? So